Okay, so now we're going to explain some memory consistency models in detail. First, we're going to look at some industry practices, some models that are being implemented in commercial products. And then we're going to look at two academic proposals. Keep in mind that the detail of the model in itself, it's not a physical constant that you have to memorize, you have to know for sure, but these are fairly typical implementations. No model is intrinsically good or bad, it's always a trade-off. They decide on what is the right interface. Remember, a memory consistency model is a contract between what the hardware implementation promises and what you can get out of from the software's side, what the perspective, what the expected outcome of a certain type of program can be. It's a contract. The more restrictive contract leads to less surprise in the outcome of a parallel program, so it's easier to program. The flip side of that is it tends to limit what you can do in terms of hardware implementation, and it can lead to slower execution. So again, we saw the problem. We saw the code over here. We see that a more restrictive, for instance, sequential consistency model that dictates every memory event has to be done before the next one can happen, and this can lead to long execution time. There's no overlapping whatsoever, but really in this particular case, and overlapping with data accesses is really not harmful. So how is this done? One very common way of implementing it is the use of memory barrier. We insert one before the flag, between the flag and data updates. The data updates over here and the flag update on the producer side. And we also insert one between reading of the data and the reading of the flag. So now these accesses can happen in parallel or concurrently, overlapping, but they cannot overlap with the flag update. And it is the programmer's job to insert these memory barriers. Now, ideally, you hope an automated process can figure this out for you. A compiler would be a good place to understand the program and insert these barriers, but in practice, I don't think this is done in an automated fashion yet. And so what can happen is you insert these at the wrong location and you still end up with incorrect result, or incorrect in the sense it doesn't correspond to your expectation. So that's really the problem, that these relaxed models is a contract. There are different versions of the contract. They're not necessarily easily understood. It's hard to explain them. You need a lot of examples to show what happens. And we will see that in one of the microprocessor alpha, the reason we use that is because it has a very well written hardware manual that is widely available. They have all these litmus tests to explain this is allowed, that's not possible. So it's a rather complicated process to understand what is allowed, what is not allowed. So, and also, since it's a contract, anybody can decide to write up one on their own. So you got all these different things from Sun. Total store ordering, partial store ordering, relaxed memory ordering. These are from Spark processors, Digital Alpha. They no longer exist, but they produced their own model. IBM PowerPC has their memory consistency model. Intel had their own model. It's called processor consistency. And of course, sequential consistency is one that people are widely in agreement about the details. These are found in actual products, and there are some which we'll cover later on. Release consistency and weak ordering, these two models are proposals from the academic side, and no real products, as far as I know, actually implemented either one. So there's no universal model. The only exception is perhaps sequential consistency. And so if you code for one type of processor, you move to another processor, you now need to know a whole new contract. And that can be painful, and it's not very helpful. Parallel programming is already difficult. So that's the problem with this relaxing model. It's just making people's life more difficult. And also, once you had this contract, it's very hard to change because of backward compatibility. You can tighten it in a newer generation. You can say we have an implementation that is more restrictive than our model allowed. That's fine, but you cannot relax it. You cannot say now our concurrency level is higher than an older program running on this newer machine would potentially get a counterintuitive result, and that's not helpful. So once you decided to do something, it's hard to go back and change it. So this led to some discussion about what you really should do, and there is some consensus that, in fact, sequential consistency might be what you want to implement. Because at least it's very clear, a lot of people understand that. I shouldn't say a lot of people understand, it's very easy to understand relative to these other models. And in fact, it's not that restrictive in hindsight. We can actually play some speculative tricks to get around many of the restrictions implied by the model. We will see that later. Okay? So this is really the general gripe about memory consistency models. The industry was a young one. We were making up these things as it goes, so some of the design decisions in hindsight looked not very optimal. So there's so many of them. How do we think about them? This is one way to look at them. It's what they're trying to do. Why are they coming up with these models? So we started with the more restrictive model, the sequential consistency. Here, you cannot reorder accesses. Okay? You have to go, every thread has to go in program order, and at any point, only one memory transaction can happen at a time. At least that's the model. A main desire is to allow read to happen sooner. Why? Because you're loading data into processor's register, and there are dependent instructions waiting for the load. So you want to load to bypass past stores, to bypass earlier stores. So if you have a store, rather than waiting for the store to completely finish, and we know that's a long process because you have to invalidate and collect confirmation from the caches that you're invalidating, that you have invalidated all the cache copies. So that's a long process. A write takes a long time. We can sit there and wait, and that's slow, or we can allow read to bypass the write, meaning even though a read is in program order after an earlier write, we already started to read it. So when we relax this ordering, we allow read and write to reorder, then we're no longer placing constraints on the read. The only thing that stays is all the stores has to be in the sequential order. So hence the name total store ordering. Okay, So after one relaxation, you get TSO. And then this is perhaps harkening back to the this example over here. Well, here I have these two stores. Do I have to order them? Well, in this case, no, right? We don't have to order them. We just have to make sure that they're done before the memory, before the flag is done. Remember that example? So that relaxation, allowing write-to-write reordering. If there are two writes, we may not strictly follow the order or follow the program order in terms of actually carrying it out. And so that led to partial store ordering. And finally, one school of thought says we might as well just not enforce any order to begin with. So, you know, you have a whole bunch of read and writes that you want to do. You may not need them to be in any particular order, but if you're writing the code down, some transaction has to come first. So that doesn't necessarily mean you want it to happen first. Why not? Why not ignore the implicit program order completely? And if you want any memory transaction to go before another memory transaction, you have to tell me explicitly. And that's actually this model over here. Okay, so you can see that this chain of models are becoming more and more relaxed, meaning the hardware implementation can be more, there's more freedom to it. Okay, and there's one extra thing that we're not talking about just yet, and it has to do with the notion of write atomicity. So all the models on the left-hand side that we have, all these models on this side, actually enforce write atomicity. Again, we'll explain that in detail. And some models on the right-hand side even got rid of those. It says, okay, we don't have write atomicity. So let's think about this. This is something that you have to read this paper, The Formal Specification of Memory Models by Sindhu et al. This is in Blackboard. The paper, you can Google it, of course, but it's already in the course material section on Blackboard. So if you consider sequential consistency, we had this model early on. You have a single ported memory, and at any time, one processor is issuing a request to it, and within one processor, memory transactions are carried out according to program order. At least that's the behavior model of sequential consistency. Total store ordering tells you, okay, you cannot imagine the hardware is doing that. If you imagine the hardware is doing that, you write some code, you run, you're going to be disappointed. You get strange result. You have to imagine that the processor is doing the following, that it allows read and write reordering. And it's about this. You can understand it as if every processor has a little bit of a store buffer over here, and this happens very often in actual implementation. Anytime you have a store, we put you into this buffer in program order. Okay, so it's a FIFO store buffer, first in, first out. Meaning an older store will enter the buffer earlier and it will be carried out earlier than a younger, later store. But if we see a younger load, we may bypass. We may bypass the load to serve the load first because it's more critical, while the store is still pending in your store queue. So that's total store ordering. And again, when we're going to the memory, at any point, only one store can go at a time. Okay, So while store A, for instance, from this processor is happening, store B over here is not taking place at the moment. So that's total store ordering. So what's partial store ordering? Well, it's a really simple change. You just get rid of the FIFO. The store buffer is a buffer. We don't necessarily guarantee that we carry out the stores in the buffer in FIFO order. We can carry them out in any order we deem fit. And so that's these three designs. So once you have a total store buffer, and you can think about this, you can write a piece of code just like the ones that we showed you, and you can argue about what can happen and what cannot possibly happen. So let's see perhaps one example, very simple example. Let's say I have this code. Thread 1 executing on one processor, thread 2 another processor, and it's very simple. Thread 1 defines A, and then the next instruction will somehow print B. Okay, so that's a read operation. You read B's value and you print it to the display. Thread 2 does the reverse. It defines B and it prints A. Now, again, this is a common assumption that we're going to use. They all start with 0. So the question is, what is an intuitive outcome of this program? Pause the video, think about it. What if I have sequential consistency? Can I see, well, you see A is either 0 or 1, B is either 0 or 1. So there are 4 possibilities, okay, in terms of A, B, 0, 0, 0, 1, 1, 0, 1, 1. What are these possible outcomes? If I have sequential consistency, what is possible? If I have total store ordering or partial store ordering, what are possible? Okay, so let's think about sequential consistency. It's really very simple. Statement 1 and 2 cannot reorder. Statement 3, 4 cannot reorder. But 1 can happen before 3, after 3, before 3, after 3 and before 4, and so on and so forth. So the interleaving we cannot control. So that really gives us these possibilities. Okay? 1, 3 or 3, 1 doesn't really matter. And then 2, 4 or 4, 2. So that's represented here. So basically in this situation, both update finished before either of the read statement. And you can obviously see that the result of this would be A equal 1, B equal 1. The other interleaving are shown over here. So in this case, 1, 2 finished before 3, 4. In this case, 3, 4 happened before 1, 2. In these cases, as we can see, one of the print happened before its update. In this case, B is printed before it's updated. So one of them is going to print out a 0. So if we enumerate all this, we run this program, and we know we're running it on a sequentially consistent machine. We run this multiple times. We'll possibly get different result. It's possible to get 1, 1. It's possible to get 1, 0. It's possible to get 0, 1. But you see, the only possible outcome, the only impossible outcome is both of them printing 0. That's not allowed. That's not possible. If that happens, you say this is crazy. Doesn't make sense. It's illogical. However, that is that is sequential consistency. What if we have total store ordering? Remember what that is. That we have no, it doesn't work. That we have these store buffers. Okay, so what can happen? Well, imagine the case over here. This is a store. Put it in a buffer. Let the read proceed. We go to memory and read B, because that's more critical. Now we read B into the register. We know it's a 0, so we read B is a 0, and then we update A at some future time. Similarly, we could do the same thing. The B equal to 1 is a store. We put it into the store buffer, and we allow the read of A to bypass. That's higher priority. Okay, we would read A equals 0. So now you see in total store buffer, in total store ordering, when we execute this piece of code, we might get the result A equals 0, B equals 0. And we might also get the 3 other results that we explained, 1, 1, 0, 1, 1, 0. So all 4 results are possible if we have total store ordering. And that's the implication to programmers. If I have this very simple code, it doesn't mean much. Usually people don't write code like that, but this is what you have to understand. So in sequential consistency, we know the outcome will not be 0, 0. In other words, if I bought your machine, I wrote this piece of code, I executed 1,000,000 times, in one time I get A0, B0. Let me exaggerate, I can sue you because you didn't implement your machine correctly. But if you give me the contract and say, I have this read and write order relaxation, it's total store ordering, I give you the exact description of what I'm doing, then this is legal. And that's what it means to programmer. And you can see, once you have this relaxed model, arguing about the logical outcome of the program is no longer that trivial, even for this very simple piece of code. We have to think. It's no longer something that is trivially obvious.